in paraxial optics. As we were talking before, that will allow us to have kind of more systematic approach to treat the optical system with many optical elements inside. So the method is based on the fact that in paraxial optics, if I have any optical system which consists of, let's say, several lenses, and now I am sending one ray which will propagate through the optical system. In every point of the system, let's say on each surface or everywhere on the system, the ray will be characterized by two numbers. These two numbers is the position of the ray, the height of the ray above the optical axis. So this is optical axis. So now I have at each point, I have height of the ray, the distance from the optical system to the ray, which is, let's say, y0, and the angle which ray makes with optical axis. So this or this angle. So for each point, the ray can be characterized by two numbers which can be written as y and alpha. And mathematically, this object is the same as column vector. So there is a known column vector in linear algebra, so the vector can be represented by set of numbers. So here we have 2D column vector. So these two numbers, since these two numbers every ray has at every position, I can define the optical system as some black box. So I don't care how many elements inside of the optical system, but what is important for me, what is the height of the ray and the angle alpha in the input of the optical system. So let's say y0 alpha 0, and what is the height and angle y1 alpha 1 in the output of optical system. So I can represent the optical system as some mathematical operator which converts the input ray into the output ray. And again, from linear algebra, such operator can be represented by 2x2 matrix. So the result of multiplication of column vector with which consists of two numbers with 2x2 matrix will produce another vector with two numbers. So it can be written, if I have a matrix which consists of M11, M12, M21, M22 elements. The result, I'm sorry, actually here it is written in opposite way. So the y, okay, this is input, this is output. So what I am looking actually is opposite. I need the output y1 alpha 1 as the result of multiplication some matrix to y0 alpha 0 vector. So this vector is an input parameter for my system. So now, this mathematical operation is well known, so that will produce y1 and alpha 1 in the following way. So I have m11 y0 plus m12 alpha 0. That will be number, this is one number which corresponds to y1, and the second number m21 again y0 plus m22 alpha 0, which will produce for me the alpha 1. So practically I have two equations which can be written y1 is equal y0 a plus whatever alpha b, but actually it's not important in this time, in this case. Okay, so this constitutes the general approach of matrix method. So I have input parameters for each ray as two numbers y0 alpha 0, and I need to know the matrix of the system, which allows me to calculate the output parameters for that ray, again in the form of y1 alpha 1, where y1 is the height of the ray above the optical axis, and alpha is the angle with respect to optical axis again. Okay, so now, of course, in order to define the matrix for whole system, that matrix will be composed from the several other matrices for where those matrices are action on each optical element inside of the matrix. Of course, we will come shortly to that point, how we will multiply those matrices. But now we will start to define the matrix for the simplest case, for example, for one refraction or one translation. So if I have the beam coming to this point, at this point the refraction happens. Now again at second point, again the refraction happens. Somewhere between these lenses there is no refraction, but the beam is just propagating in free space, so it means some translation happens from one point to another, and so on. So now we will start to define the simple matrices for each case, and we will start from the translation matrix. So now we will define the matrix for the simplest case when the ray is propagating in a free space, or actually it can be in some medium as well, and it's passing through 2 points A and B. Let's say this is 2 points between, so it's propagating between surface of 2 optical elements inside of the optical system. And here, so let's say this is a distance L. At point 8, A, the ray is characterized by its height y0 above the optical axis and some angle alpha 0. The same for the point B. It is characterized by position y1 above the optical axis and angle alpha 1. So now I can write that in the output of the system, the vector representing the beam position is y1 alpha 1, and it is equal some matrix times y0 alpha 0. So now I want to find the matrix which is called in this case the simple translation matrix. So let me remind you the multiplication rules of matrix times vector. So I have A1, A2, A1, A2. So which is A1 is the component of the vector which I am multiplying. So I am looking it in a form. Let me separate it. So I will have two numbers. I will have A1 which is Y0. I will have A2 which is alpha 0. I have A1 which is Y0. I have alpha 0 here. And this number must be equal to Y1, and this number must be equal to alpha 1. So how I am going to do it? Y1 from this triangle is simple equal Y0 plus L, which is a distance, times alpha 0. Basically it is times tangent of alpha 0, but in paraxial approximation we are saying that the tangent of alpha is approximately equal to alpha. Here, in order to make this expression equal to alpha 1, I can multiply this to 0 plus and multiply alpha 0 to 1, since alpha 1 is equal alpha 0. And one more step, I need to multiply these to 1 to keep this expression true. So now I have four elements, 1, 0, L, and 1, which is representing my matrix. So I can write y1 alpha 1 is equal, the matrix is 1, L, 0, 1, alpha, y0 alpha 0. And this matrix which we found is a simple translation matrix. So now we will define the matrix which is corresponding to refraction on a single spherical surface. So let me draw a picture. So here is the spherical surface with refractive index n prime inside of this medium and the refractive index n outside of that medium. And here I have perpendicular to the surface. So this point is C, which is the center of the sphere corresponding to this surface, and R is the radius of the surface. And now I have the ray coming to this point. So this angle is alpha 0, and since this is the perpendicular to the surface, this angle is theta angle, which is angle of incidence. Now after the refraction, the ray is changing direction, and now this theta prime is the angle of refraction. And so if I draw a line which is parallel to the optical axis. So this is my optical axis, and this is the line parallel to the optical axis. So this angle, if this angle is phi, this angle is also phi, this angle is phi, this angle is alpha 0, and now this angle is alpha 1. So the height of this point above the optical, so the distance to the optical axis, is y0. So but the same, so the y0 for the incoming ray, but for outgoing ray this is exactly the same point. So y0 is equal y1. And now I need, so I have alpha y0 alpha 0, y1 alpha 1. So y0 alpha 0 corresponding to the in matrix form corresponding to incoming ray, and alpha. So I am looking for the matrix which converts incoming ray to outgoing ray. So I will have the expression y1 alpha 1 is equal m times y0 alpha 0, and my answer I am expecting in the form m11 y0 plus m12 alpha 0. This will be number which equal y1, and this part which is equal alpha 1 will be in the same form, m21 y0 plus m22 alpha 0, and that will be alpha 1. So, and I need to find these four coefficients of the matrix. So obviously from here, since y1 is equal y0, because we are talking about the same point, we have this coefficient is equal 1, this coefficient is equal 0. Now I need to find these two coefficients, so I need to write alpha 1 in the form of some term. One consists of y0 and another term consists of alpha 0. For that one, I will consider these two angles. So from this set of angles, alpha 0 is equal theta minus phi, and alpha 1 is equal theta prime minus phi. So now the theta and theta prime are connected with Snell's law. So I can write that n theta is equal n prime theta prime, from where theta prime is equal n over n prime times theta. In addition, I can find theta from this expression. So theta is equal alpha 0 plus phi. But what is phi here? I can find it from these three angles. So I have y0, and this side in paraxial approximation is approximately equal also r. And now I can find, I can write that, or actually I can find, I don't need even this R, this approximation, because I have that y0 over r is equal sine phi, but since y0 over r is equal sine phi, which is approximately equal phi. So now I have the theta is equal alpha 0 plus y0 divided by r. And now I can write alpha 1 is equal theta prime, which is n over n prime times theta plus minus phi, which is minus y0 over r. And now if I am using this expression for theta, I have n over n prime alpha 0 plus y0 r minus y0 r, which I can rewrite in the form of n over n prime alpha 0 plus 1 over r, or y0 over r, n over n prime minus 1. So now this is what I was looking for. So I can write that alpha 1 is equal 1 over r n over n prime minus 1 y0 plus n over n prime alpha 0. So obviously this will give me m21, this will give me m22 coefficients. And now as the final step I can rewrite this equation. So I have y1 alpha 1 is equal, so I have the matrix with 4 coefficients. These two is 1 and 0, and this coefficient is 1 over r n over n prime minus 1, and the last n over n prime times y0 alpha 0. So this is the matrix which corresponds to the refraction on the spherical surface. It is easy to show that if the radius becoming infinity, what does it mean? It would correspond to the refraction on planar surface. So if I have planar surface, alpha 0, alpha 1, this is alpha 0, again y0 is equal y1. So what will change in this matrix? This element becoming 0 because r becoming infinity. So practically we found the refraction matrix for planar and for spherical surface as well.